Welcome to Module 7 of the Maggot Sensing Systems Industrial Vibration Training Course, Diagnostics Part D. In this module, we will cover fault frequencies and alarms. Mechanical fault frequencies are determined by the physical makeup or design of the equipment being monitored. These fault frequencies are related to the running speed of the equipment. If the running speed increases, the frequency at which the fault will manifest itself in the vibration spectrum will also increase. Mechanical fault frequencies can usually be calculated by understanding the components and their interactions. Types of mechanical fault frequencies include gear mesh, blade pass, vane pass, coupling frequencies, belt frequencies, and bearing defects. The mere presence of mechanical fault frequencies does not necessarily indicate a problem. Let's look at an example of calculating fault frequencies. Here we have a typical double reduction gear set. There is an input shaft, an intermediate shaft, and an output shaft. There are 2 sets of mating gears and 4 gears total. There are several frequencies that will be generated by the gear set. They include, but are not limited to, the input or shaft 1 speed, intermediate or shaft 2 speed, output or shaft 3 speed, gear mesh frequency for gears 1 and 2, and gear mesh frequency for gears 3 and 4. It is important to understand that any of these frequencies can be evident at any measurement location on the gear set. We can calculate the gear mesh frequency if we know 2 pieces of information, the shaft speed and the number of teeth on the gear. With this information, we can determine the speed of the other shafts and the other gear mesh frequencies. In our example, we have an input shaft rotating at 1780 RPM with a gear mounted on this shaft with 25 teeth. We can calculate the gear mesh frequency 1 by multiplying our shaft speed, 1780 RPM, times the number of teeth on the gear, 25, to get a gear mesh frequency 1 of 44,500 CPM. Now that we know the gear mesh frequency 1, and we know the number of teeth on the mating gear, we can calculate the intermediate or shaft 2 speed. To get the shaft 2 speed, we take the gear mesh frequency 1 and divide it by the number of teeth on the mating gear mounted on shaft 2. In our example, we would take 44,500 and divide it by 60 teeth. This gives us a shaft 2 speed of 741.66 RPM. We can now use the same method we used previously to determine the gear mesh frequency 2. In our example, we would take our shaft 2 speed, 741.66 RPM, and multiply it by the number of teeth on gear 3, which is 35. This gives us a gear mesh frequency 2 of 25,958.33 CPM. Finally, we can calculate the speed of the output shaft, or shaft 3. To calculate the shaft 3 speed, we take our gear mesh frequency 2, which is 25,958.33, and divide it by the number of teeth on the mating gear, gear 4, which has 70 teeth. This gives us an output shaft speed of 370.83 RPM. Planetary gearboxes are fairly unique in design, and to determine what frequencies are associated with them, it is important to understand the components and how they operate. A planetary gearbox is comprised of 4 main components: the sun gear, which is the main gear, planet gears, which are attached to the carrier, which connects to the planet gears and rotates in the opposite direction of the sun gear, and the ring gear. Planetary gearboxes will generate several frequencies which may be present in a vibration spectrum. These frequencies include sun gear RPM, planet gear RPM, carrier RPM, sun gear mesh frequency, planet gear mesh frequency, and the dominant gear mesh frequency. It is normal for these frequencies to be present in the spectrum and do not necessarily indicate a problem. However, changes in amplitude can be an indication of a problem. If we know the mechanical makeup of the gearbox, we can calculate what frequencies are going to be generated. First, let's look at the sun gear mesh frequency. If we know the speed of the sun gear and the number of teeth on the gear, we can determine the sun gear mesh frequency. The formula is sun gear mesh frequency equals the sun speed times the number of teeth on the sun gear. In our example, we would take 1782 RPM, the sun gear RPM, and multiply it by 16, the number of teeth on the sun gear, which gives us a gear mesh frequency of 28,512 CPM. Next, we need to calculate the ratio. We accomplish this by adding the number of teeth on the ring gear to the number of teeth on the sun gear, and then divide the total by the number of teeth on the sun gear. So for our example, we would add the ring gear teeth, 32, to the sun gear teeth, 16, for a total of 48, and then divide that number by the number of teeth on the sun gear, 16. This gives us a ratio of 3. Now that we know the ratio, we can calculate the carrier speed. The formula for calculating the carrier speed is the sun speed divided by the ratio. So for our example, we would take the sun speed of 1782 and divide that by our ratio, which is 3. This gives us a carrier speed of 594 RPM. Remember, the carrier rotates in the opposite direction of the sun gear. Next, we can calculate the planet gear speed. To calculate the planet speed, we divide the number of ring gear teeth by the number of planet gear teeth. We then take this quantity and multiply it by the carrier speed. So in our example, we would take the ring gear teeth of 32 divided by the planetary gear teeth of 8 to get 4. We would then take 4 and multiply it by our carrier speed, which is 594 RPM. This gives us a planet gear speed of 2,376 RPM. Now that we know the speed of our planet gear, we can calculate the planet gear mesh frequency. To calculate the planet gear mesh frequency, we multiply the planet speed by the number of teeth on the planet gear. In our example, we would multiply 2,376, the speed of our planet gear, by 8, the number of teeth on our planet gear, to get a planet gear mesh frequency of 19,008 CPM. The last frequency we will calculate is the dominant gear mesh frequency. The dominant gear mesh frequency is calculated by multiplying the planet gear mesh frequency by the number of planet gears. In our example, we would take 19,008, our planet gear mesh frequency, and multiply it by 3, the number of planet gears, to get a dominant gear mesh frequency of 57,024 CPM. Blade or vane pass frequencies can be easily calculated. Simply take the number of blades or vanes and multiply it by the running speed of the machine. The mere presence of these frequencies does not necessarily indicate there's a problem. However, changes in amplitude can be due to mechanical problems. Jaw-type couplings will generate vibration related to the number of jaws the coupling has. To calculate this frequency, we simply take the number of jaws and multiply it by the machine RPM. It is important to understand what vibration jaw-type couplings generate because it is often the same frequency other machine faults might appear at. This is when it is most important to truly understand the machine and what is causing the vibration. It is normal to see some vibration at the jaw coupling frequency. Be careful not to mistake this with misalignment. An increase in amplitude over time can indicate a problem. Belt-driven machines will often have a belt frequency evident in the vibration spectrum. We can calculate at what frequency the belt vibration will occur. To calculate belt frequency, we would multiply 3.142 times the pulley RPM times the pulley diameter, and then divide this total by the belt length. There are a couple of things you should keep in mind here. The RPM used in the calculation and the pulley diameter need to be from the same pulley. The pulley diameter and the belt length need to be in the same units. If you use inches for one, use inches for both. And lastly, it is normal to see some vibration at belt frequency. However, changes in amplitude can indicate a problem. Chain frequency can be calculated by simply multiplying the number of teeth on a sprocket by the RPM of that sprocket. It is common to see chain frequency vibration on chain-driven equipment. There are essentially 4 kinds of bearing defects that can generate a vibration response in the spectrum. Ball pass frequency outer race, which is a defect on the outer race of the bearing. Ball pass frequency inner race, which is a defect on the inner race of the bearing, cage frequency or fundamental train frequency. This will typically show up as a modulating frequency around ball pass frequency outer race or ball pass frequency inner race, and ball spin frequency, which is a defect on the roller elements themselves and often is a result of other damage. For reference purposes, I have shown the formulas for calculating the bearing defect frequencies. However, it is not common that you should have to actually calculate these frequencies yourself. Most vibration analysis software will contain a database with the bearing defect frequencies defined by bearing manufacturer and model number. Most softwares will also allow you to add bearings to the database if you have a special bearing. The bearing defect frequencies can usually be obtained directly from the manufacturer of the bearing if not found in the database. One of the most common problems any analyst will eventually run into is fault frequencies that just don't line up exactly. This can be caused by a couple of different factors. The bearing selected from the database may not be the exact bearing. This can happen as manufacturers may change the design of a given part or obsolete parts. At times, the data becomes inaccurate. Also, different manufacturers have the same or similar part numbers, but the bearing geometry may be very different. Because the bearing defect frequencies are non-synchronous harmonics of a running speed, small errors in the reference speed can throw off our defect frequencies, especially at higher multiples. For example, if our reference speed is 1800 RPM from the nameplate, but with slip, the motor actually runs 1780, our defect frequencies will not line up exactly. At the 10th bearing harmonic, we will be off by over 1300 CPM. It is important to get as accurate a speed reference as we can. Wear can also cause bearing defect frequencies to shift slightly. This is less common than other causes, but can still be a factor. As a bearing wears, the clearance of the bearing becomes larger. This change in the geometry will shift the bearing defect frequency slightly over time. Electrical fault frequencies will only be generated if the equipment is running. There are two types of electrical faults to consider. Speed dependent, meaning that they are derived from some mechanical makeup of the electrical system, such as rotor bars, stator slots, or poles. There are also speed independent frequencies such as line frequency or SCR firing frequency. VFD drives will have a variable line frequency because the line frequency is varied to control the speed of the motor. Electrical frequencies will disappear when the equipment is de-energized. Rotor bar pass frequencies can be calculated by taking the number of rotor bars on the rotor and multiplying it by the rotational speed of the rotor. The stator pass frequency can be calculated if you know the number of stator coils in the motor. This is not common information and can be difficult to obtain. To calculate stator pass frequency, we multiply the number of stator coils by rotational speed. Pull pass frequency can be calculated if we know how many pulls the motor has and the amount of slip that is occurring. For example, we know that an 1800 RPM rated motor has 4 pulls. If the actual running speed of the motor is 1780 RPM, then our slip is 20 CPM. So we can calculate pull pass frequency by multiplying 4 pulls by our slip frequency of 20 CPM. This gives us a pull pass frequency of 80 CPM. Keep in mind that pull pass frequency will most often be seen as sidebanding of other frequencies. 2 times line frequency is generated by the number of pulls pulling on a given rotor location during one full rotation. A 4-pole motor operating at 60 Hz rotates at 1800 RPM. So to determine 2 times line frequency, we take 1800 times 4 pulls and get 7200 CPM or 120 Hz. A 2-pole motor operating at 60 Hz rotates at 3600 RPM. Our 2-time line frequency can be calculated by taking 3600 RPM times 2 pulls, and we get 7200 CPM or 120 Hz. With variable frequency drives, the motor speed is controlled by varying the frequency of the applied voltage. The same principle is applied in that the 2 times line frequency vibration is created by the number of pulls pulling on the rotor at a given location during a full revolution. Because the line frequency is varied to achieve the desired speed, we must determine the line frequency being applied each time we want to identify our 2 times line frequency. In our example, we have a motor running at 1755 RPM. To accomplish this, the AC line frequency is actually 58.5 Hz, not 60 Hz. So to calculate 2 times line frequency, we take 58.5 Hz and multiply it by 2, or take our running speed, 1755, and multiply it by 4 to get 7020 CPM, or 117 Hz. There are 2 types of SCR frequencies that may be present on a DC motor. Whether it is a half-wave rectified or a full-wave rectified motor will determine which frequencies you will see. For a half-wave rectified motor, the SCR frequency will be 3 times line frequency. For a 60 Hz system, this is 10,800 CPM. For a full-wave rectified motor, the SCR frequency will be 6 times line frequency. For a 60 Hz system, this will be 21,600 CPM. One of the most common questions that comes up in the world of vibration is how much vibration is too much. This is a very difficult question to answer as there are many factors that need to be considered. For example, how fast is the machine running? Is it a reciprocating machine? What type of base mounting is being used? And what is the function of the machine? For this reason, there are many varying opinions about what the appropriate vibration levels are. Several organizations have attempted to define alarm criteria for rotating equipment, and these can be a good place to start when setting up a new program. The most common standards are published by ISO. There are different standards for different equipment types. Other companies have published alarm criteria as well, such as Technical Associates of Charlotte. Often large companies like Cargill and GE will undertake setting their own alarm criteria based on their process and specific needs. There are 2 primary types of alarms that can be used. Overall alarms, which look at the total amount of energy within a given frequency range, and spectral band alarms, which allow the user to set several specific frequency alarms to better identify specific faults. Spectral band alarms can be fixed in amplitude, alarm off of a change over a baseline, or use statistical process to determine the alarm level. We will discuss each of these further in the coming slides. An important consideration when setting alarms is what units of measurement to set the alarms in, and for that matter, what units the data is collected in. This is particularly important for faults that may occur at frequencies below 600 CPM or above 60,000 CPM. If a desired alarm occurs below 600 CPM, it may be better to use displacement as the units, as it will be more sensitive to changes at that frequency range. If the desired alarm occurs above 60,000 CPM, acceleration may be the best units. For everything in between, it is likely that velocity will be the preferred units. Overall alarms can be obtained using different methods. This is a big part of why all overalls from different data collection devices do not match exactly. The overall vibration level can be obtained using data collector hardware designed to detect the overall vibration, or can be calculated using the software, typically from the spectral data. When using the data collector hardware, the overall may be calculated using a fixed range determined by the data collector, or sometimes the user can determine what the frequency range to be used. When the software is used, the range is typically a bit more flexible. It can be set to the full range of the measurement or a specific range defined by the user. Often the software overalls are calculated from the spectral data. Each method of collecting the overall vibration value has its advantages and disadvantages. Spectral band alarms use a vibration value derived from a spectrum. The user typically sets the lower frequency cutoff and the upper frequency cutoff, and only the energy within the defined range is used for the alarm. This method allows for more focused alarms that can be specific to a particular type of fault, such as bearing frequencies, while ignoring other frequencies that could cause false alarms like gear mesh. One of the advantages of using spectral band alarms is the ability to have several alarms, each set for a specific type of fault. When calculating the spectral band levels, there are primarily 2 ways to go about it. Absolute threshold, which sets a maximum allowable vibration limit, and if any one peak within the frequency range exceeds this threshold, an alarm is triggered. The other method is using a power band. This type of alarm will take the total energy within a given frequency range. The important difference is that no one peak has to exceed the alarm level to trigger an alarm. If the collective energy exceeds the alarm level, an alarm will be triggered. This is particularly useful with faults like bearings, where the amplitude of each bearing defect harmonic may not be excessively high, but the number of harmonics can certainly be an indication of a more severe problem. Many software packages will have several options for how to set a band alarm. Fixed alarms allow the user to set a specific threshold for an alarm, and it does not change. The band value is then compared to this level to determine if an alarm condition exists. This can be used with absolute threshold or power band alarms. A delta alarm allows the user to set a known good reference as a baseline, and a percentage of increase over that baseline is set as the alarm level. With this type of alarm, it is very important to have a good baseline. Statistical alarms look at the data collected over time and then calculates an alarm based on a standard deviation from the statistical average. This can be helpful if you have no idea where to start with alarms. However, large changes in machine condition have to be accounted for in the averaging, especially after repair, or alarms can be inaccurate. It is important to review alarms periodically to ensure they are effective. When reviewing alarms, we want to determine if the alarms are set too high and are not catching problems as they occur. We also want to determine if alarms are set too low, causing nuisance alarms that do not really require maintenance action. And lastly, we want to ensure that if machine conditions have changed, such as a change in process, speed changes, or load changes, that our alarm limits are still valid. When dealing with slow speed equipment, there are often special considerations that are needed to ensure accurate alarming. This generally applies to machines where the frequency of interest will be below 600 CPM. There are three factors we need to consider: transducer roll-off, data collector roll-off, and velocity roll-off, if the measurement is in velocity. The transducer and data collector roll-off you will need to get from the manufacturer of your particular make and model. The velocity roll-off can be calculated. I call it a severity ratio, and it is calculated by taking the frequency of interest and dividing it by 600. We can use a formula to determine what our low-frequency alarm should be based on these considerations. To calculate the new alarm levels, we take the alarm levels that we would use above 600 CPM, multiply that by the severity ratio, and then by the percentage of remaining signal from both the instrument roll-off and the transducer roll-off. Let's look at an example. Here, our normal vibration would be set to 0.4 inches per second. In this case, we want to alarm off the running speed, which is 30 RPM. For the purposes of this example, we will assume an analyzer roll-off of 30% and a transducer roll-off of 5%. When you do these calculations yourself, you will need the specific data for your make and models. So first we calculate the severity ratio by taking our running speed of 30 and divide that by 600, which gives us a ratio of 0.05. Since we assumed a 30% roll-off on the analyzer, we will have 70% signal remaining, which will be represented in our equation by 0.70. Since we assumed a 5% roll-off for our transducer, we will have 95% signal remaining, which we will represent in our equation as 0.95. So our new alarm level is calculated by taking 0.4, our previous alarm, multiplying it by 0.05, our severity ratio, and then by 0.7, our instrument roll-off, and then finally by 0.95, our transducer roll-off. This gives us a new alarm setting of 0.0133 inches per second. You have just completed Module 7, Diagnostics Part D. This completes our series on industrial vibration analysis. We hope you have found these presentations helpful, and you can contact us anytime at 1-800-WILCOXEN or at www.wilcoxen.com.